What's up, guys? Mr. Moore here. We're going to do a little review for the quarterly test, or as people pointed out, it's the quarterly test. Let's see. It should be some kind of R in there, I think. So, number one, a car is traveling 40 meters due east in 5 seconds. And we have another car that's traveling 64 meters due west in 8 seconds, and you have to figure out these cars during their period definitely had the same which. So it's not displacement because one car went 40, the other went 64. Right. It's not average velocity because velocity is a vector, and vectors imply direction. So these cars are going different directions, so they have different velocities. Momentum, we haven't even talked about that yet. So it's got to be speed, and if we look 40 meters in 5 seconds, so this was going 8 meters per second. Likewise, 64 meters in 8 seconds, so this car was also traveling 8 meters per second. Remember, speed doesn't have a direction. So number two, the distance time graph at the right represents the motion of a lab cart. According to this graph, the cart is which? So if the distance versus time graph looks like this, then its velocity time graph would look something like this, and its acceleration time graph would be nothing. So it would be 0. It would look something like that. So this is the first kind of motion. We've talked about this before. This is something that's traveling at a constant speed, a constant velocity. All right, this would be like a car in cruise control. So according to this graph, this cart is moving at a constant speed. All right, number three, the graph at the right represents the relationship between distance and time for an object in motion. During which interval is the speed of the object changing? So we're looking at a distance versus time. We need to figure out when its speed is changing. Well, let's look right here. From A to B, all right, there's no increase in distance. So from A to B, this object is not moving at all. From B to C, the distance is increasing, but this is kind of like the example before. So this is kind of like question number two. If distance versus time is increasing like this, that implies that it has a constant velocity, and a constant velocity is not a changing speed, right? So this is kind of like a constant speed right here from B to C. C to D, well, now the object is not increasing its distance, so here the object isn't moving, therefore its speed is not changing. And finally we have D to E, so in this case we see a parabolic shape, right, a curved shape, and that implies that its velocity is increasing. So it's going to be number four. All right, number four, the graph represents the relationship between distance and time for an object moving in a straight line. According to the graph, this object is. So here we have another distance versus time graph. So I'm going to draw the velocity time graph and the acceleration time graph for this as well. So when we see a shape like this, this implies a constant acceleration. And in constant acceleration, the velocity is changing with time. So the velocity is increasing with time. And in this case, acceleration is what's constant. So two types of graphs you need to memorize. You need to memorize this set right here, constant speed, right? This is called like a car in cruise control, constant speed. And then there's this set, which is something that it's accelerating. So like someone who's sprinting, right? The acceleration is constant, the velocity is increasing, and the distance is increasing exponentially. So let's move on. So number five, which graph represents the same motion of an object? So in this case, we have distance, all right, displacement is increasing exponentially. The velocity is increasing linearly. This is constant acceleration. So the answer actually is this one. But let's look at the other one. So in this case, its displacement is increasing, but it has a negative velocity. So if a negative velocity, the graph really should look something like this. Its displacement would be decreasing. Here's my red. Come on now. It should look something like that. In this case, the displacement is decreasing, but the velocity is increasing, so these graphs don't match up. In this case, the displacement is slowing down, and then it's reversing direction, so this velocity is not appropriate for it as well. This would be something like that. So how about number 6? The graph represents the relationship between speed and time. So now we're looking at a speed versus time graph. This is different. And what's the total distance traveled by the object during the first 4 seconds? So if we want to get distance from a speed versus time graph, we have to calculate the area underneath. So we want from 0 to 4 seconds. So we need to calculate this area right here. Area of a triangle is 1/2 base times height. The base is 4. The height is 0 to 20, so the height is 20. And it's 1/2 base times height, so that's 80 times 1/2 is going to be 40. All right, let's do one more page of problems, and then I'll set up a new video. So again, number 7, the graph represents the speed against time, and the distance, total distance traveled by the object during the first 4 seconds is, well, this is going to be the same method as before. If we want to calculate distance from a speed versus time graph, we need to calculate the area underneath the curve. So it's a triangle, so 1/2 base times height. Base equals 4. And we have the height equal to 2. So 4 times 2 is 8. 8 times 1/2 is 4. And here we go. 8, determine the graph below represents the relationship between speed versus time. So we have a speed versus time graph of a car moving in a straight line. The magnitude of the car's acceleration is. So now we're looking for acceleration. And this is where we'll have to turn to our reference table. We know that the formula for acceleration is delta V over t. All right. Delta V is really the final velocity minus the initial velocity over time. So let's look. The final velocity is 30. The initial velocity was 0. So this is equal to 30 minus 0 over time, and we went from 0 seconds to 3 seconds. So that's 3. This should be a 0. 30 minus 0. So in the end, we just get 30 over 3, which is equal to 10. So we have 10 meters per second.